Okay, so last time we had the modulus. We defined it to be the absolute value of the complex number z equals a plus bi. It's that distance away from the origin in the complex plane. We talked about graphing a number a. Suppose I want a greater than or equal to 0. Okay, put that line right here. So it's greater than or equal to 0. That's my imaginary plane, and that's my real axis. I want the numbers that are to the right of 0. We also talked about if I have an imaginary axis and a real axis, and I want the values of b that are greater than 0. A can be anything, but b has to be greater than or equal to 0. I want these ones up here this time. Okay, we'll want those ones right there. That'll give us the values of the complex numbers who have an imaginary value that is greater than or equal to 0. Okay, the ones that are less than 0 are down below. Okay, suppose I want the values of the complex number z such that the modulus of z is equal to 1. That means its distance away from the origin is 1. Hold on one second, gotta answer that. Okay, so if we want all the complex numbers in the world that have a modulus equal to 1, what we're looking for is all the complex numbers whose distance away from the origin is exactly 1. So you can think of it like a string of length 1, and if you wrap it around this complex origin, you'll get this. How is that different than the next one? Well, the next one is all the ones that have that string or less than it, that distance away from the origin or less than that, less than or equal to 1. So we'll get a situation where we have all those values in the middle. All right, so we talked about it in the complex plane. Let's talk about them having, be able to talk about them in the polar form. So a complex number has polar form or trig form. Z equals r times cosine theta plus I sine theta, where the modulus r, which is defined with the absolute value z, is equal to the square root of a squared plus b squared, and tangent of theta equals b over a. So r is the modulus, theta is the argument of z. So let's write 1 plus I as a complex number in its trig form. So we're going to need a couple things. We're going to need r, and we're going to need theta, aren't we? Okay, let's figure it out. 1 plus I, again we go 1 on the real axis and 1i on the imaginary. We're going to get some value here, right? Okay, so what do we know? Well, we know if this is a plus bi, a has to be 1 and b has to be 1. So you know a is 1 and b is 1. So r is equal to the square root of a squared plus b squared, which is equal to the square root of 1 squared plus 1 squared, which is the square root of 2. We know r is the square root of 2. What else do we know? We know tangent of theta equals b over a. So tangent of theta equals b over a. Then we know tangent of theta equals 1 divided by 1, which is 1. And we know that theta must equal pi over 4, because tangent of theta equals pi over 1 happens at pi over 4. So now we have our two things that we need. We needed r, we needed cosine of theta, we have theta equals pi over 4. So we substitute into this formula right here. We substitute the value of r, and we substitute the value of theta, and we get z equals the square root of 2 times cosine of pi over 4 plus I sine of pi over 4. So that's 1 plus I in trig form. Okay, now we're going to do negative 4 root 3 minus 4i. So first off, let's find out what r is. How do we find out the value of r? Well, r again is equal to a squared plus b squared, the square root of that guy. So what do we know about a? Well, a is the value here, negative 4 root 3. You square that and you get 16 times 3 is 48, is that right? Plus the value of b squared, so 16. I think if you add those two, what do you get? You get 64, is that right? So r equals 8. So we know that r equals 8 in this equation. So we have r equals 8. Now what we need to do is find tangent of theta. That will give us what theta is, okay? So tangent of theta equals, oh, by the way, before we do this, where is this value? So we go negative 4 root 3 on the real axis, and we go negative 4i. We're over here in this quadrant, okay? Our value is somewhere over here. So tangent of theta equals equals b over a. So I'll have negative 4 root 3 over negative 4, which turns out to be what? Oh, sorry, b over a, excuse me. So tangent of theta equals negative 4 over negative 4 root 3. Cancel out negative 4, so I have 1 over root 3. Rationalize the denominator, I think you get root 3 over 3. So tangent of theta equals root 3 over 3. When does that happen? Well, that happens over here at theta equals 7 pi over 6, so it's a pi plus another pi over 6. Okay, 7 pi over 6. So now we have the value of theta, we have the value of r, we can put it in our complex form, okay, our polar form. So we put in r is 8, and we have theta equals 7 pi over 6, we put that here, and we'll get this, where can I write this thing? Write it here. I'll write z equals 8 times cosine 7 pi over 6 plus I sine 7 pi over 6. Okay? So that's the polar form of these two complex numbers. Okay, so now we're going to talk about multiplying and dividing complex numbers. So if we have z1 equals r1 cosine of theta plus I sine theta 1, and z2 equals r2 cosine of theta 2 plus I sine of theta 2, then we can say that the product of these two is multiplying these two. We do this guy times this guy, r1 and r2, get r1 and r2. And then if we multiply these two, okay, what we're going to do is we're going to use our formula, right? Sine of a sum or cosine of a sum or sine of a difference, cosine of a difference. And we simply get cosine of theta 1 plus theta 2 and I sine of theta 1 plus theta 2. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. We use those rules to say that the product of these two equals this and the quotient of these two equals this. Now what I want to do is actually want to show the product of these two equals this. Okay, so I'm going to take z1 and z2, I'm going to multiply them, use that rule, and get that. Let's take a look. So if I have z1 times z2, then that means I'm going to have r1 cosine of theta 1 plus I sine theta 1 times r2 cosine of theta 2 plus I sine of theta 2. So this will equal r1, r2, right? That's the product of r1 and r2. And then these two, since it's a sum, I got a FOIL, and so I'll have, keep that outside, and I'll have cosine of theta 1 times cosine of theta 2 plus, that's those two. I'll do this one times this one plus I sine theta 2 cosine theta 1, and again this is going to be a little bit bigger. I gotta get this a little bit bigger. Plus this one times this one, I sine theta 1 cosine theta 2 plus this one times this one. I times I is I squared. I squared is equal to negative 1. So it'll actually be minus sine theta 1 sine theta 2. So now if you look at this one, cosine, cosine, sine, sine, right? What's that mean? If I go cosine, cosine, sine, sine, that's equal to our cosine formula. So this will equal r1, r2, okay, and that'll be cosine of theta 1 plus theta 2. That's this value, this one in green is this one here, okay? And then in orange, I have sine, cosine, cosine, sine. So that's sine, that's adding, so it'll be plus, I'll have I sine of theta 1 plus theta 2. Okay? So what's that say? The bottom line is that what that says is that if we want to multiply two complex numbers, what we do is we multiply the moduli and add the arguments. So again, we multiply the moduli and add the arguments. That's all that says, okay? And you can do a similar argument for the division of them as well. All right, let's take a look at an example. An example here, we're going to multiply z1 times z2. So again, multiply, moduli. So 2 times 5 is 10. Okay, and then we're going to take this. So that's our 10. Put this in parentheses. We're going to have plus I. Now what we do is, again, when we want to multiply two different complex numbers, the simple rule is multiply the moduli and add the arguments. So we'll just simply say this is going to be cosine of the sum of these two, and this will be sine of the sum of these two. Pi over 4 plus pi over 3, it's like 1/4 plus 1/3, you can add fractions. Turns out to be 7 pi over 12 for both cases. Okay, so now we got de Moivre's theorem, okay? So we talked about how to add and subtract and multiply and divide complex numbers in polar form. Well, here's how you raise them to a power. So when we want to raise them to a power, it's this theorem here. For if z is r times cosine theta plus I sine theta, it's a polar form, okay? Then of a complex number, then for any integer n, z to the n is equal to the modulus, okay, to the n, times cosine of n theta plus I sine theta. Why the heck is this thing true? This is a great question. So the way I'm going to show this is I'm simply just going to do this. If we let z equal, what do I have? You can't really see that, can you? Give it color. There we go. If I have z equals r times cosine theta plus I sine theta, then if I multiply both sides by z, then I multiply the left side by z and the right side by z, well, multiply the left side by z, I get z squared. This is z, so I multiply it times itself, so I have r cosine theta plus I sine theta times r cosine theta plus I sine theta. Okay? Well, r times r is r squared. And when we multiply, remember, we just add the arguments. So I'll have cosine of, add the arguments, theta, and theta is 2 theta, plus I theta, and theta is 2 theta. Okay, we talked about this just a second ago. Okay? So that's r squared. Well, fine. What about z cubed? What's z cubed equal? Well, multiply the left side by z, multiply the right side by z. So this will equal r squared. This is the left side, or the right side, cosine 2 theta plus I sine 2 theta. Okay, that's this. And I'm going to multiply it by z. What's z? R cosine theta plus I sine theta. Okay? R squared times r is r cubed. Add the arguments. Cosine 2 theta, cosine theta is cosine 3 theta. Okay? Sine 2 theta, sine theta, sine 3 theta. We add the arguments. Okay? Now if you generalize, look, if I have 1, I got 1, and I got 1 of those and 1 of those. And I got 2, I got 2 of those, and 2 of those, and 2 of those. And I got 3, I got 3 of those, and 3 of those, and 3 of those. So therefore, you can generalize, using induction, we won't talk about it, z equals r to the n, z to the n equals r to the n, cosine of n theta plus I sine of n theta. Okay, we just did exponents, now I've got to do roots. So the nth roots of the complex numbers, if z equals r times cosine theta plus I sine theta, and n is a positive integer, and then z has n distinct roots, n distinct nth roots, wk. So we'll have n of them, so there's n of them here. This is n of them, right? Right. 1, 2, 3, 4, 5, 6, whatever, then that's the last one. N minus 1, n. There's n roots here. So you have w0, w1, w2, w3. That's what k is. Okay, so it'll have n distinct nth roots given this form. Okay, so let's take a look at an example about how to do this, to work with this, and see how it works.